Hello there, and welcome to tonight's slow journey. If you found this place between wakefulness and sleep, you're in the right hands. Tonight we drift outward, past familiar nights and rooftops, beyond the map of our small blue world, toward one of the universe's quietest, deepest mysteries, the black hole. We will move gently, one breath at a time, through the strange and patient logic that governs these objects. We will learn not with pressure but with ease, letting each fact settle like a warm stone in your mind. If you enjoy these quiet wanderings, consider liking or subscribing. It helps others find their way here too, one sleepy listener at a time. But for now, settle in, let your body unwind. Breathe slowly in and out. Feel your lungs expand and soften. Let your eyes grow heavy. We begin gently at the edge. What is a black hole? A calm map of invisible gravity. A black hole is a place where gravity has won so completely that space itself folds in on a point. Imagine a weight on a stretched sheet. The heavier the weight, the deeper the well. Keep breathing slowly as we picture that well. At the center of a black hole, the well becomes infinitely deep in our current equations, a point where our usual rules blur. But the simple, peaceful idea to hold is this. A black hole is a region where gravity traps everything that crosses a boundary. That boundary is called the event horizon, the point of no return. Outside that boundary, light and matter behave more or less as usual, and we can watch from a careful distance. Inside, all paths lead inward. The black hole hides whatever is inside from outside observers, and that gives it the name. Not because it's merely dark, but because even light cannot escape. So when you relax tonight, imagine a hill of space curving downwards, gentle on the outside, absolute at the center. The mathematics that describe this, the equations of Einstein, tell a precise story, a quiet geometry of curved space-time, and that geometry is what we call a black hole. Black holes are not monsters in stories. They are simple consequences of mass and gravity cooperating under the rules of the universe. Anywhere enough mass gathers tightly enough, gravity may win. When that happens, a new region of space-time is formed, a black hole. And while that central point has puzzled physicists for decades, the event horizon gives us enough to understand their outer life, how they bend light, how they accrete matter, how they shape galaxies. Tonight, those behaviors are our gentle companions. Birth of a stellar black hole, the quiet death of a giant star. Most black holes begin with an ending, the slow, patient life of a massive star. Imagine a star many times heavier than our sun. For millions of years it burns, balancing gravity's inward pull with heat from nuclear fusion pushing outward. When its nuclear fuel fades, that balance falters. In a quiet but unstoppable collapse, the core caves inward. Outer layers may explode away as a supernova, a bright crashing bloom of light and dust. What remains may be a compact remnant, a neutron star, or, if the core is heavy enough, a black hole. The formation is violent on cosmic scales, but in narration it can be imagined as a surrender. Heat fades, gravity wins, and matter compresses into a new, tiny geometry. The newborn black hole is initially cloaked by the shocked gas and dust of the supernova remnant. Over thousands or millions of years, that shroud clears, leaving the black hole as a silent, invisible presence, detectable only by the way it tugs on nearby. Stars or lights surrounding gas into brilliant X-rays as material, spirals inward. In binary systems, where two stars orbit each other, the collapse may leave one star feeding the other's remnant, creating some of the brightest X-ray sources in the sky. So tonight, as you breathe, picture a great star whose last exhale becomes the seed of a black hole, a quiet transformation that folds part of the star back into space, leaving a small but powerful gravity well. Supermassive black holes, the slow anchors of galaxies. At the hearts of nearly every large galaxy reside black holes millions to billions of times the sun's mass. These are the supermassive black holes, ancient and steady, their growth paced over cosmic time. They sit like slow anchors, influencing star orbits in their immediate neighborhoods and, through dramatic outflows and energetic episodes, sometimes shaping the larger galaxy. How did they form? The story is still under study, but the calm fact to hold is that they grow by eating gas, swallowing stars, and merging with other black holes. As galaxies collide and merge, their central black holes can meet and coalesce, gradually building mass. Observations show that the mass of a galaxy's central black hole correlates closely with the mass of the galaxy's central bulge of stars, a quiet sign that galaxies and their black holes evolved together. Supermassive. Black holes are not always actively dining. For long stretches they are tranquil, almost invisible, felt only by the slow orbital motion of nearby stars. Then sometimes a stream of gas or a wayward star wanders in, sparking a bright episode called an active galactic nucleus. But over the long arc of time, these giants exercise a kind of administrative gravity, shaping the flow of gas and influencing when and where stars are born. Tonight, let your thoughts rest on the image of a slow, immovable heart at the center of a city of stars. The heartbeat is faint, measured not in seconds but in millions of years, and yet its influence is profound. The event horizon, the gentle boundary of no return. The event horizon is the defining edge of a black hole. It is not a solid surface but a geometric boundary. Cross it, and no signal can return to the outside world. For a distant observer, the horizon is where time appears to slow and light appears to redden, as photons struggle to climb back out of the gravity well. Imagine a pebble sliding down a bowl toward the center. As it approaches a particular rim within the bowl, the slope steepens and escape becomes impossible. That rim is like the event horizon. From a safe distance you might see the pebble approach forever, its motion slowing to a crawl. But in the pebble's frame, it crosses in finite time and continues inward. Physically, the size of the event horizon, called the Schwarzschild radius for a non-spinning black hole, scales directly with the black hole's mass. For a black hole with the mass of our Sun, the radius would be only a few kilometers. For a supermassive black hole, the radius can be as large as our solar system. Picture an invisible sphere, larger or smaller depending on mass, that quietly sets the limit for escape. The event horizon also gives us the beautiful concept known as the black hole's surface area, which relates to entropy, a measure of hidden information, a fact we will return to later softly and slowly. Tonight, breathe with the horizon, a boundary that is absolute yet invisible, a gentle line that divides two kinds of space-time. Accretion disks and the slow music of falling material. Many of the most luminous black hole phenomena come from matter that orbits the hole before falling in. When gas and dust approach, they typically carry angular momentum, a kind of cosmic spin. That material flattens into a disk, swirling closer and closer, heated by friction and magnetic forces. These accretion disks can glow across the electromagnetic spectrum, from visible light to X-rays, depending on how hot they become. The physics inside an accretion disk is both turbulent and elegant. Viscous processes, often mediated by magnetic fields, allow gas to shed angular momentum and drift inward. As it does, the gravitational energy of falling matter converts into heat and radiation. For supermassive black holes, these disks can span light years and be brighter than the combined light of all a galaxy's stars during active phases. For smaller stellar mass black holes, the disks are compact but intensely hot. Jets, narrow beams of plasma launched perpendicular to the disk, sometimes appear, streaming outward at near light speeds across intergalactic distances. The exact mechanism for jet formation remains a subject of lively research, but it likely involves magnetic fields twisted by the rotating disk and the black hole's spin. The sight of a quiet black hole contrasted with a brilliant, humming accretion disk is one of the universe's great visual contrasts. Serene geometry around a storm of incandescent matter. As you relax tonight, imagine the slow whirl of an accretion disk, not chaotic, but patient, a circular procession of atoms spiraling inward, shedding tiny bits of energy, singing a faint electromagnetic song as they go. Spin in the ergosphere, the stirring of space-time. Some black holes rotate. In fact, many do. When a black hole spins, it drags space-time around with it in a phenomenon known as frame dragging. Close to the event horizon, this twisting of space creates a region called the ergosphere, an oblate bubble outside the horizon where nothing can remain at rest relative to distant stars. The ergosphere is a place of subtle opportunity. Because space-time itself is being dragged, clever physical processes can extract energy from the black hole's rotation. The Penrose process, a theoretical idea, describes how a particle entering the ergosphere can split, sending one piece into the hole, while another escapes with more energy than the original. In astrophysical settings, magnetic fields and plasmas realize similar extraction processes, and they may power the most powerful jets we observe. Spin also influences the shape of the innermost stable orbit, the last circular path matter can take before plunging in. A fast spinning hole allows matter to orbit closer, liberating extra energy, and producing even hotter, brighter disks. When we detect rapidly varying X-ray signals or luminous jets, spin is often a central suspect. As you breathe slowly, picture space-time itself as a viscous syrup rotating around the black hole. Everything within the ergosphere carried along, a subtle dance of geometry and energy that is both precise and poetic. Tidal forces and spaghettification, the stretching of bodies when matter approaches a black hole, gravitational gradients, tidal forces, pull harder on the nearer side than the farther side. For small black holes, the gradient near the horizon can be enormous, stretching objects into long, thin strands in a process playfully named spaghettification. For a person falling feet first into such a black hole, the difference in pull between feet and head would be extreme, but not all black holes are murderous in that way. Around supermassive black holes, the event horizon may lie so far from the center that tidal forces there are mild. An astronaut crossing the horizon of a million solar mass black hole might feel no immediate stretching. The crossing could occur calmly, with extreme effects only occurring much later. So the sensation of tidal force depends on scale. Small black holes can shred near the horizon, while very large ones can hide their violence deeper inside. Tidal forces also shape the light we see. As a star approaches a black hole and is gradually pulled apart in a tidal disruption event, its gas wraps into a luminous stream, briefly lighting the black hole's surroundings. These transient flares are one way we identify dormant black holes that otherwise hide in galactic centers. Tonight, imagine gentle stretching like honey pulled slowly on a spoon, not frightening, but a quiet illustration of how gravity can act differently across small distances. Time dilation and gravitational redshift. Clocks that slow. One of the soothing peculiarities of gravity is its effect on time. Near a massive object, clocks run slower compared to clocks far away. This isn't a metaphor. It's a measured fact from Einstein's theory of general relativity. For a black hole, this effect becomes dramatic. As you approach the event horizon, a distant observer would see your clock slow, your motions draw out, your light redden and fade. From your own perspective, you cross the horizon in finite proper time, unaware of anything singular at that boundary. But to an external watcher, your approach seems to freeze, your image smeared into an ever-dimming halo close to the horizon. Light climbing out loses energy, shifting toward redder wavelengths in a process called gravitational redshift. This interplay between perspectives, finite time for the infaller, stretched time for the distant observer, is one of the universe's gentle paradoxes. It reminds us that simultaneity is not absolute, and that the flow of time depends on where and how you sit in space-time. If you breathe slowly now and let your sense of time soften, imagine clocks thinning and yawning, each tick taking longer as the gravity grows. Hawking radiation, the whisper that black holes can glow, 1974. Stephen Hawking showed that black holes are not perfectly black. When quantum effects are included near the event horizon, particle-antiparticle pairs spontaneously form, and sometimes one falls in while the other escapes, creating a faint thermal glow we call Hawking radiation. This process assigns a temperature to a black hole, inversely proportional to its mass. The smaller the black hole, the hotter it becomes. For astrophysical black holes, those formed from stars or weighing millions of suns, the Hawking temperature is unimaginably low, lower than the cosmic microwave background, so they effectively gain mass from the surrounding radiation instead of losing it. Only tiny hypothetical black holes would radiate noticeably. Over incredibly long timescales, though, Hawking radiation implies that black holes can slowly evaporate, leaking mass back into the universe. This soft quantum whisper links gravity to quantum mechanics and gives black holes a thermodynamic life. They have temperature and entropy. The entropy, proportional to the horizon area, suggests that information about what falls in might be encoded on the surface. This idea, that geometry and information meet at the horizon, is one of our gentle invitations toward deeper mysteries. Tonight, picture the black hole breathing almost imperceptibly, a faint, quantum exhale that will, over unimaginable time, change its mass. Gravitational waves and the music of merging holes. When two black holes spiral inward and merge, they send ripples through spacetime, gravitational waves. These are distortions that travel at the speed of light, stretching and squeezing space as they pass. The Laser Interferometer, Gravitational Wave Observatory, LIGO, first detected these waves in 2015. A quiet chirp from a cataclysmic merger, billions of light-years away. The waveform of a merger, a slow, deep in spiral, a crescendo as the holes coalesce, and a ringing final tone as the merged black hole settles, encodes precise information, the masses, spins, and distance of the system. These events have become tools for astrophysics, revealing populations of black holes, testing general relativity, and opening a new sense. We can now listen to the universe's most violent dances. Mergers are elegant in their finality. Two objects lose orbital energy by radiating it away, draw closer, and combine into a single, distorted black hole that radiates the last asymmetries as gravitational waves until it relaxes into a steady, spinning form. The music of these waves is quiet by human standards, but our instruments translate them into audible chirps. Imagine listening in the dark to a distant, precise chord, the universe rearranging itself with calm inevitability. Imaging the shadow. What we can see of the invisible black holes are invisible, but their surroundings are not. In 2019, the Event Horizon Telescope produced a groundbreaking image, the shadow of the supermassive black hole in M87. This image did not show the horizon directly, but rather a dark silhouette against a glowing ring of accreting gas, curved and lensed by the black hole's gravity. The shadow is shaped by the photon sphere, a region where light can orbit temporarily, and the strong lensing of rays near the horizon. The bright ring we see is light emitted by hot gas, bent around the hole and focused toward us. The exact shape of the shadow can tell us about the hole's spin and orientation, while the ring's brightness reveals dynamics of the disk and jet-launching regions. That image marked an era. We can now both listen to and image black holes. In the future, improved arrays may reveal time-varying details, allowing us to watch matter swirl and hotspots orbit near the horizon. For tonight, hold the image of a black silhouette encircled by a luminous ring, a perfect visual metaphor for the invisible, made visible by patient global effort. Black holes and galaxies, architects of cosmic structure. Black holes are not isolated curiosities. They co-evolve with their host galaxies. Active episodes can inject enormous energy into the surrounding gas, quenching or stimulating star formation. Powerful jets can sweep away gas from galactic centers or compress it into dense regions where stars might form. Observations show links between central black hole mass and galaxy properties, hinting at an ongoing dialogue across cosmic ages. These feedback processes are subtle and long-term. A black hole that feeds too greedily can heat the galactic gas, preventing it from cooling and forming new stars. Conversely, a calmer black hole allows gas to settle into cold clouds and spawn new generations of stars. So galaxies and their black holes appear as collaborators, shaping each other's futures through exchanges of energy and matter. Imagine a slow gardener tending a vast field, sometimes pruning, sometimes turning soil, sometimes stepping back. The black hole is that gardener on galactic scales, quietly regulating the ecosystem of stars and gas over millions of years. The information puzzle, whispered secrets and modern ideas. Of the deepest questions about black holes concerns information. What happens to the detailed information about matter that falls in? Classical general relativity says it vanishes behind the horizon. Quantum mechanics insists information cannot be destroyed. This apparent contradiction spurred decades of debate, culminating in ideas that the information may be encoded on the horizon or emitted slowly via correlations in Hawking radiation, or conserved in some holographic boundary description. Physicists propose a delicate reconciliation. Perhaps the horizon stores the information as subtle correlations, like writing with a microscopic font on the surface area, or perhaps the interior is encoded in a different, dual description of spacetime altogether. These ideas are abstract, mathematical, and far from settled, but they highlight a hopeful point. Black holes force us to re-examine the foundations of space, time and information. Tonight, rest with the notion that knowledge may be preserved in unexpected ways, that the universe, while hiding, may also be keeping careful notes. Exotic ideas, primordial holes, charged holes and wormholes, beyond the ordinary categories lie speculative, but constrained possibilities. Primordial black holes could have formed in the newborn universe from extreme density fluctuations, tiny holes that might contribute to dark matter or evaporate via Hawking radiation. Theoretical solutions also permit charged or highly spinning black holes with different geometries and inner structures. Wormholes, tunnels connecting distant regions, appear in some mathematical solutions, often requiring exotic matter to remain open. While these ideas capture the imagination, they remain speculative. The calm truth is that they expand the conceptual landscape, showing the mathematical richness of general relativity and the quantum theories that aspire to replace it. As you drift, let imagination wander, but remain anchored in what observations tell us. The universe is big enough for both verified subtleties and wild conjectures. Both kinds of thought expand our sense of possibility. Observing and listening to black holes, how we keep company with the invisible, our instruments, our patient listeners and patient viewers. We detect black holes by watching stars orbit unseen masses, by observing bright X-ray accretion disks, by capturing gravitational waves, and by imaging the shadows of nearby giants. Each method reveals a different layer: dynamics of orbits, thermal glow of inflowing plasma, the space-time ripples of mergers, and the silhouette of the shadow. Future progress will come from more sensitive detectors, longer baselines of telescopes, and improved theory. Multi-messenger astronomy, combining light, gravitational waves, and perhaps neutrinos, promises an even richer conversation. But for tonight, the essence is simple. We are not shut out from black holes. We keep company with them through clever observations and the patient accumulation of evidence, slowly learning their ways. So breathe once more and let the last image settle, an invisible well of gravity, quiet and patient, wrapped in luminous halos and subtle signals. It is an object that teaches us humility, that even the darkest corners of reality are comprehensible in their own terms. Let those thoughts ease your mind as you drift deeper into sleep, where the universe's slow stories continue, untroubled and grand. Quantum gravity, where the fabric frays near the center of a black hole, our familiar physics begins to tremble. General relativity describes spacetime beautifully on large scales, and quantum mechanics governs the small. But inside a black hole's depths, the two theories meet and disagree. The singularity is a place where density grows without limit, and our equations falter. It is a mathematical signpost that says, here the map ends. Scientists believe a more complete theory, quantum gravity, will someday smooth this frontier. Whether it's string theory, loop quantum gravity, or something not yet imagined, such a theory would describe how space-time itself behaves when it becomes granular, when geometry is quantized, when even distance and time become uncertain. For now we can only imagine. Perhaps the singularity is replaced by a finite, dense core. Perhaps space-time bounces. Perhaps black holes are not dead ends but gateways in the topology of the universe. None of this is yet known. What is known is that nature has left us a gentle puzzle, a place where two great descriptions whisper to each other, but do not yet agree. As you breathe softly, imagine space-time as a fabric woven from tiny threads of probability, vibrating, subtle and patient, and at the heart of the black hole, those threads tremble together in perfect silence. Binary black holes and the choreography of cosmic pairs, black holes rarely live in solitude. Many are found in pairs, orbiting each other in quiet, tight circles that shrink over time as they lose energy through gravitational waves. These binary black holes perform a long, slow dance, millions of years of silent revolution before their final embrace. When they merge, their horizons fuse in a brief flicker of unimaginable energy. The resulting black hole rings like a bell, emitting gravitational waves that fade as it settles into equilibrium. Each event is a line in the cosmic symphony LIGO and Virgo are now recording, the low hum of space itself being stirred. The orbits of binary black holes can be eccentric or perfectly circular. Their spins can align or misalign depending on how they formed, from stellar binaries or chaotic collisions in dense star clusters. Each detail adds nuance to the pattern of the waves we detect. As you drift, imagine two invisible spheres circling, closer and closer, space rippling around them like water around sinking stones. Their final moment is not an explosion, but a merging, two gravities becoming one, and silence following the crescendo. Black holes and dark matter, the unseen companions. Dark matter is one of the great unknowns of cosmology, invisible, pervasive, shaping galaxies yet refusing to shine. Could black holes be part of it? Some theories suggest that primordial black holes formed in the infant universe might account for a fraction of dark matter. Others say the dark matter halo surrounding galaxies helps feed and grow central black holes. Observations test these ideas gently. The distribution of matter in galaxies, the gravitational lensing of light, and the patterns in the cosmic microwave background all place limits. So far, black holes alone cannot explain dark matter. But the two mysteries, dark matter and black holes, remain curiously intertwined, both invisible, both massive, both shaping the cosmic web. In a deeper sense, they are companions in the unseen, one bending light locally, the other sculpting the large-scale structure of the universe. As telescopes and detectors improve, we may learn whether their stories overlap, whether dark matter is particulate, primordial, or something stranger still. Breathe slowly now and imagine a night sky laced with invisible threads, dark matter binding galaxies, black holes weighting their centers, two forms of the unseen holding the visible universe in balance. The slow death of black holes, evaporation and the end of time. Even the mightiest black holes are not eternal. Over vast timescales, Hawking radiation ensures that they will evaporate, losing mass one whisper at a time. For stellar mass black holes, the process is beyond slow, longer than the age of the current universe. But in the far, far future, after the stars have died, after galaxies have dimmed, only black holes will remain, slowly fading into nothing. This distant era is called the black hole era, part of the universe's long cooling toward entropy's end. As black holes radiate their last quanta, they return their energy to space. When the final black hole evaporates, the universe will be left in near-perfect darkness, filled with a thin mist of photons and neutrinos, a silent equilibrium. There is beauty in that slowness. The universe began in fire and will end in quiet. Black holes born from collapse will be the final storytellers, whispering energy back into the cosmos until even they are gone. If you close your eyes now, you can imagine it, not sadness, but completion, the universe exhaling after an age-long breath. Reflection, what black holes teach us about ourselves in the end. Studying black holes is less about the objects themselves and more about our need to understand. These invisible wells of gravity show us the limits of knowledge and the humility of curiosity. They remind us that mystery is not failure. It is an invitation. Every image, every waveform, every equation carved on a chalkboard is a small light cast into vastness. Black holes teach patience. They evolve over eons. They show that what is unseen can still be real, that silence can still hold structure, that darkness can still teach. As you breathe your last few breaths tonight, let these thoughts settle, that the same laws governing the spin of galaxies also cradle the atoms in your hands, that your heartbeat and the pulse of quasars follow rhythms born from the same physics, that within every question about the universe lies a quiet reflection about what it means to wonder at all. So drift now, slowly, gently, knowing that the universe continues its patient unfolding, and that somewhere far beyond the stars, black holes keep their silent watch, holding the memory of everything that was. The cosmic web, gravity's grand design. The universe is not random. On the largest scales, galaxies and clusters trace out a vast lattice, a cosmic web woven from filaments of dark matter and light. Between these strands are immense voids, nearly empty expanses that span hundreds of millions of light-years. Gravity sculpts this web. Tiny fluctuations in the early universe grew under its pull, gathering gas, stars, and galaxies into vast structures. Simulations like Illustris and Millennium have shown us the delicate filigree of creation, threads of matter, stretching and branching like neurons in a cosmic brain. Black holes sit at the nodes of this web, anchoring galaxies and regulating their growth through jets and radiation. In this way, the invisible dance of gravity links the smallest scales to the largest, from the horizon of a single black hole to the horizon of the entire universe. So breathe deeply and imagine yourself floating within that web, a single point of consciousness suspended in the grand architecture of existence. Quasars, the blazing hearts of darkness in the early universe. Galaxies often hosted active, furious centers, quasars. These were supermassive black holes devouring gas so quickly that the infalling matter heated to millions of degrees, outshining entire galaxies. A quasar is paradox incarnate, a beacon born of darkness. The accretion disk glows. Jets burst outward at near-light speed, and magnetic fields twist into shapes we barely comprehend. Yet at the heart, beyond the light, lies silence, the event horizon. When we observe distant quasars, we are looking back billions of years, seeing the universe as it was when it was young and restless. Over time, as their fuel ran out, many quieted, leaving only dormant black holes behind, sleeping giants at the centers of galaxies, including our own. Let the thought ease you. Even the brightest fires fade into peace. Even the most chaotic beginnings calm into stillness. The center of our galaxy, Sagittarius A, at the heart of the Milky Way lies Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. Hidden behind clouds of dust and gas, it sits 26,000 light-years away, quiet yet powerful. In 2022, the Event Horizon Telescope revealed its shadow, the dark silhouette surrounded by glowing plasma. It was the second black hole ever imaged after M87 Keeks, and it confirmed once again Einstein's predictions. Around it, stars orbit at breathtaking speed. One, named S2, completes a full orbit every 16 years. These motions allow astronomers to test relativity in the most extreme environment known. Yet for all its gravity, Sagittarius A is gentle now, accreting only small drifts of matter. A calm heart in a spiral of 200 billion stars, the galaxy hums around it like a living organism, its center steady and patient. Close your eyes and picture it, a serene presence, invisible, but holding everything in balance. Our galaxy's quiet anchor, time near the abyss, relativity in motion near a black hole, time itself stretches. The closer you approach the horizon, the slower clocks tick relative to faraway observers. This is gravitational time dilation, one of Einstein's most elegant predictions, and one that has been confirmed again and again. If you could hover safely just above a black hole, an hour for you might be decades for someone far away. Light climbing out of the gravity well would shift to red, losing energy as it escapes. To an outside observer, it would seem as if you were frozen, forever falling. But from your perspective, time would continue, normal, intimate, unbroken. This strange elasticity of time is not illusion. It is the geometry of reality. Black holes remind us that time and space are not separate. They are threads of one fabric, curving together under gravity's hand. Let that thought settle as you drift. The seconds you feel are your own, and the universe itself breathes in rhythms slower and grander than we can imagine. The language of light, how we decode the invisible. We never see black holes directly. Instead, we listen to light, to its colors, its timing, its polarization, its echoes. Astronomers use X-rays, infrared, radio waves, and even gravitational waves to piece together a full portrait. Each wavelength tells a different story. Radio waves reveal jets and magnetic fields. X-rays trace the hottest matter spiraling inward. Infrared peers through dust to the galactic core. Gravitational waves carry the rhythm of collisions. Together they form a symphony, a multi-messenger chorus of the cosmos. Even silence speaks. When expected emissions vanish, it tells us something about the environment. So when you look up at the night sky, remember, every twinkle, every flicker, every faint hum of radiation is part of a grand conversation, the universe talking to itself, and we, the quiet listeners. Spin. The black hole's hidden identity. Every black hole has three defining properties: mass, spin, and charge. Charge usually cancels out, leaving mass and spin as the main fingerprints. Spin, or angular momentum, can twist space-time itself, creating frame dragging, where space and time are pulled along like syrup around a spoon. Near a rapidly spinning black hole, this effect becomes profound. Orbits flatten and jets align along the rotational axis. Some black holes spin almost at the theoretical limit, near the speed of light. Others, slowed by mergers or accretion, rotate more gently. Measuring spin helps scientists uncover how black holes formed, what they've eaten, and how they've evolved. Imagine, as you rest, the slow rotation of the cosmos itself, galaxies turning, stars orbiting, electrons spinning, from the smallest to the greatest, all in quiet harmony. The edge of knowledge, singularities and censorship. At the core of a black hole lies the singularity, where density becomes infinite and known physics breaks down. Some theories propose that quantum effects will prevent the singularity from truly forming, a concept called cosmic censorship, hiding the breakdown of laws behind the event horizon. No one knows for sure. Some models suggest a Planck star, a compact region where gravity and quantum mechanics balance each other. Others hint at wormholes or bounce scenarios, where collapsing matter may re-emerge elsewhere. For now, the singularity remains a metaphor for mystery itself, the horizon of understanding. When we say we don't know, we are not defeated. We are alive to the wonder that reality is richer than our equations. As you breathe in and out, remember, the unknown is not darkness. It is simply the part of the map that waits for light. The echo of the Big Bang, cosmic background whispers all across the sky, faint microwave radiation hums, the cosmic microwave background, CMB. It is the afterglow of the Big Bang, fossil light from when the universe was just 380,000 years old. Tiny fluctuations in this radiation seeded all later structure, including black holes, galaxies, and stars. By studying the CMB, we measure the universe's age, shape, and composition. Even black holes leave their subtle imprint upon it, through gravitational lensing and the integrated Sachs-Wolf effect, slightly altering the background's smoothness. So when you hear of background noise in astronomy, think of it as a lullaby older than any star, a cosmic cradle song still echoing from the moment everything began. Dark energy, the quiet acceleration for decades. Astronomers thought the universe's expansion would slow over time, but observations of distant supernovae revealed the opposite. The expansion is accelerating. Something unseen, called dark energy, is pushing galaxies apart. Dark energy makes up nearly 70% of the universe, yet we do not know what it is. It could be a property of space itself, a cosmological constant, or a new field that changes with time. Whatever its nature, it will shape the universe's fate. In billions of years, galaxies will drift beyond each other's light, and the night sky will grow emptier. But right now we live in a moment of balance, where stars still shine, where light still travels, where understanding still grows. Let that thought soothe you. The universe is expanding. Yes, but so is knowledge, compassion, and the quiet wonder that connects all who gaze upward. Hawking radiation. When black holes whisper light for decades, black holes were thought to be eternal, traps from which nothing could escape. Then, in 1974, Stephen Hawking discovered something astonishing. Through quantum effects at the event horizon, black holes slowly emit radiation. Tiny pairs of virtual particles, flickering in and out of existence, become separated, one falling in, the other escaping as real energy. This process, now called Hawking radiation, means black holes can slowly lose mass and eventually evaporate. For a stellar black hole, this would take longer than the age of the universe, but for smaller, hypothetical ones, it could happen faster, ending in a burst of energy. It's one of physics' most beautiful paradoxes. The darkest object in the universe still shines, faintly, through the laws of quantum mechanics. Even in silence, nothing is truly lost. Wormholes, shortcuts through space-time. Einstein's equations allow for strange possibilities. One of them is the wormhole, a tunnel through space-time connecting distant points. The idea was first imagined in 1935 by Einstein and Rosen, the Einstein-Rosen bridge. In theory, a wormhole could link two black holes, or even two universes. In practice, such a structure would collapse instantly unless held open by exotic matter, a form of energy with negative pressure, something we've never observed. Still, the mathematics are sound, and in modern physics and science fiction alike. Wormholes represent hope, that distance, time, and separation may not be limits, but puzzles waiting to be solved. As you rest, imagine drifting through such a tunnel, falling not downward but between places. Light stretching, stars bending, reality folding in gentle curves. The universe whispering shortcuts in its geometry. Dark matter, the invisible scaffolding. All the stars, planets, and gas we see make up less than 5% of the universe. The rest is hidden, most of it as dark matter unseen but known through gravity's pull. Galaxies spin too fast to hold together by visible mass alone. Something unseen anchors them. Dark matter neither emits nor absorbs light, but it forms the skeleton upon which all structure is built. Halos that cradle galaxies, filaments that shape the cosmic web. We've searched for it in underground detectors, in particle accelerators, and in the motion of galaxies. We don't yet know what it is, perhaps weakly interacting massive particles or something stranger still. But we feel its presence. The night sky itself is balanced upon its invisible frame. You, too, are balanced upon unseen supports. Faith, love, memory, the dark matter of the human heart. The far future, when the stars go out, if time were allowed to run forward, unimaginably far, trillions of years, the universe would fade into quiet. Stars will burn out. Galaxies will dim. Black holes will outlast them all, slowly evaporating through Hawking radiation, until even they dissolve into faint heat. Physicists call this the heat death of the universe, a time when all energy is evenly spread and nothing more can happen. No light, no structure, no sound. Just a thin sea of particles forever expanding. And yet, even this is not tragedy. It is peace on a cosmic scale. The universe, having sung its great song of stars, ends not with violence but with rest. So let that calm you. All things that begin must also fade, but fading is not failure. It is simply another form of stillness, the same stillness you feel now as you breathe in the quiet. The information paradox. Can black holes forget? When matter falls into a black hole, what happens to the information it carried, the structure of atoms, the quantum states, the memory of what it once was? Stephen Hawking once believed it was lost forever. But that idea defied quantum theory, which insists that information can never be destroyed. This conflict between relativity and quantum mechanics became known as the black hole information paradox. Physicists like Leonard Susskind and Juan Maldacena proposed solutions. Perhaps information is preserved in subtle quantum correlations or encoded on the event horizon itself, a concept called the holographic principle. If true, then every black hole is a cosmic hard drive, storing its entire history on its shimmering surface. The universe may never forget. The holographic universe. When reality is a projection, from the information paradox came a breathtaking idea. Maybe our entire universe is holographic. In this model, everything we experience, space, time, energy, could be a projection from a distant boundary, like a 3D image cast from a 2D film. The idea isn't fantasy. It arises naturally from string theory and black hole thermodynamics. If this is true, then black holes are not anomalies, but windows, revealing that reality itself may be encoded on a cosmic screen. Every movement, every particle, every thought might already be written there, shimmering on the edge of space. So breathe slowly, and imagine you are both inside the projection and part of the light that casts it. White holes, the other side of darkness. If black holes pull everything in, then what if there existed their opposites, objects that only expel matter and energy? Physicists call them white holes, theoretical time reverses of black holes. Nothing can enter a white hole, only leave. They might represent the birth phase of a black hole, or even be connected to them through wormholes, forming bridges across time. No white hole has ever been observed, but their equations fit cleanly into Einstein's framework. If they exist, they could explain cosmic phenomena we cannot yet name, or even the birth of our own universe. Perhaps, somewhere in the deep cosmos, a white hole is still blooming, not devouring, but creating. Quasars, the blazing hearts of galaxies at the centers of galaxies. Some black holes feast so violently they become quasars, engines brighter than entire galaxies. As gas spirals inward, friction and gravity heat it to billions of degrees, emitting jets of radiation that travel millions of light years. Quasars show us the universe as it was billions of years ago, young, fierce, and luminous. The light that reaches us now began its journey before Earth even formed. In the quiet of night, those faint glimmers in the telescope are not stars, they are black holes on fire, galaxies in their infancy, and history still arriving at your eyes. Time dilation, falling through eternity close to a black hole, time itself slows down. To a distant observer, an object falling toward the horizon seems to freeze, never quite crossing, its final moment stretched into eternity. But from the falling object's own view, it crosses the horizon smoothly, unaware that to the rest of the universe, it has become timeless. This is time dilation, one of Einstein's most beautiful predictions. Black holes teach us that time is not constant. It bends, flows, and stretches depending on gravity. So as you rest, remember, even time is flexible. Every second you feel is part of a larger rhythm, the slow heartbeat of space-time itself. The galactic center, Sagittarius Aursu, at the heart of the Milky Way, 26,000 light-years away, lies a supermassive black hole, Sagittarius Eta, 4 million times the mass of the Sun. Invisible yet powerful, it anchors our galaxy's stars in orbit. We've seen its influence for decades, stars whipping around it at immense speeds. In 2022, the Event Horizon Telescope revealed its shadow, a glowing ring of gas, orbiting the unseen. Every night you look at the center of the Milky Way, you're gazing in its direction, toward the silent gravitational heart that holds us all. We are, in a very real sense, orbiting the invisible. Spaghettification, the ultimate stretch inside a black hole's gravitational field. The pull on your feet could be millions of times stronger than the pull on your head. The result is spaghettification, matter stretched and thinned by tidal forces until it becomes streams of subatomic particles. Though it sounds brutal, it's simply gravity doing what gravity does, drawing everything along the steepest curves of space-time. For small black holes, this happens quickly. For supermassive ones, you could cross the horizon peacefully before being torn apart inside. It's the universe's quiet way of saying, all things eventually yield to curvature. The Event Horizon Telescope, imaging the invisible for decades. Black holes were purely theoretical, equations, not images. Then in 2019, humanity saw the unseeable, a glowing ring around a shadow. The first ever photo of a black hole, M87, captured by the Event Horizon Telescope. It took a planet-sized array of radio telescopes and petabytes of data, synchronized across continents. When the image appeared, it confirmed Einstein's predictions almost perfectly. That blurry orange halo was not just science, it was poetry. For the first time, we looked into darkness and found understanding. Gravitational waves, ripples in reality. In 2015, LIGO detected the first gravitational waves, ripples in spacetime from two merging black holes 1.3 billion light-years away. The signal lasted less than a second, but it changed physics forever. For the first time, we didn't just see the universe, we heard it. A faint chirp from across the cosmos, the vibration of merging gravity itself. Now, every new detection adds a note to the growing symphony. Neutron stars, black holes, cosmic collisions, space playing its own music. Listen quietly, and perhaps somewhere the universe is still humming. Primordial black holes, relics of creation. Not all black holes are born from dying stars. Some may be primordial, formed in the first seconds after the Big Bang, when density fluctuations could have collapsed directly into miniature black holes. They might still drift through galaxies, tiny but massive, as ancient fossils of creation itself. If we could find them, they might even explain part of dark matter. Imagine that, the oldest things in the universe. Invisible travelers born before the first stars, still moving among us. The cosmic web, gravity's grand design. The universe is not random, it's structured. Galaxies are connected by immense filaments of gas and dark matter, forming the cosmic web, the largest pattern in existence. At every node of this web sits a galaxy cluster, often with a supermassive black hole at its heart. These black holes regulate growth, shaping how stars form and galaxies evolve. From the smallest atom to the grandest web, gravity links it all. You are part of that same network, a node of thought in a web of being. Accretion disks, the light before darkness. When matter falls toward a black hole, it doesn't fall straight in. It spirals, forming a glowing accretion disk that shines across the universe. X-rays, ultraviolet, and light so intense it outshines galaxies. These disks are laboratories of extreme physics, magnetic fields, turbulence and temperatures beyond comprehension. They remind us that before darkness consumes, it always burns brightly. Black hole jets, light launched from darkness. Paradoxically, black holes, now the darkest entities in space, create some of the brightest phenomena. Relativistic jets. Streams of plasma erupt from their poles, traveling near the speed of light, powered by twisted magnetic fields. These jets can stretch for millions of light years, shaping galaxies and distributing heavy elements across space. From the deepest gravity wells comes creation. Darkness gives birth to light. Entropy and the arrow of time. Black holes are the universe's greatest engines of entropy, disorder. Each one holds the maximum possible entropy for its size. As they absorb matter, they increase the universe's total disorder, pushing time forward. Entropy gives time its direction, from order to chaos, from birth to decay, from beginning to end. Black holes are the milestones of that journey. They remind us time does not flow backward because the universe remembers. When gravity grows too strong, black holes are the final perfection of gravity. Near them, the pull becomes absolute, a curve of space-time so deep that nothing can resist it. If one were to wander close to our solar system, the first changes would not be violent but subtle. Planetary orbits would stretch and drift, tides would swell beyond their usual rhythm, and the moon's dance around Earth might slightly tremble. For a while, the universe would remain deceptively calm until the curve deepened further. It is a reminder that immense change often begins quietly, with the gentlest tug of invisible threads. The edge of disruption. The solar system's harmony is a delicate clockwork. If a black hole passed within a few light years, its gravity could nudge that balance, sending comets spiraling inward or pushing planets into new orbits. Astronomers call this a gravitational perturbation, a soft rearranging of cosmic furniture. Even then, the black hole itself might remain unseen, its presence betrayed only by shifting starlight and the faint murmur of bent trajectories. It teaches us how even unseen forces can reshape entire worlds. The dance of distortion. Closer still, the light of the stars would begin to bend. Gravity acts not only on matter, but on the very path of light itself. Say a black hole moving through the sky would create a shifting lens, stretching constellations into halos, duplicating their images like reflections on rippling water. This phenomenon, gravitational lensing, is both beautiful and eerie. If one ever passed near Earth, we would see the heavens shimmer strangely, not destruction but distortion, as space-time itself became a living mirror. The silent tidal pull. The real danger of proximity lies not in suction, but in differential gravity, the difference in pull between one side of a body and the other. If Earth drifted too close, the planet would feel the stretching known as tidal force. It is the same mechanism that moves our ocean tides, amplified to cosmic extremes. Rocks would rise like slow waves. Oceans would lean toward the dark horizon. It sounds apocalyptic, yet it is also pure physics. The graceful consequence of gravity doing exactly what gravity does. Even destruction in this view is just another form of natural balance. The glow before the fall, before anything crossed the event horizon, it would shine. Matter spiraling inward forms an accretion disk, heating to millions of degrees as friction turns potential energy into light. This glow would outshine galaxies. To distant observers, the Earth might appear as a spark, fading into a brilliant whirl of radiation, brief but breathtaking. This is how astronomers detect black holes in faraway systems, not by what is lost, but by what blazes before the silence. The boundary of no return. At the event horizon, even light itself cannot escape. This boundary is not a surface but a threshold, a place where escape velocity equals the speed of light. For anything crossing it, time slows to near standstill. To an outside observer, the fall seems endless, frozen at the edge. Inside, time continues, but in a direction that always leads inward. The danger here is absolute, yet it is not chaos, it is order taken to its logical limit. The universe drawing a perfect boundary between knowing and unknowing. The radiation that whispers, though black holes consume, they also emit. Through Hawking radiation, born from quantum effects near the horizon, they slowly lose mass over eons. A black hole is not eternal. It evaporates, whisper by whisper, photon by photon. Even their danger has an end, dissolving back into light and heat across unimaginable ages. It is a soft paradox. The darkest object in the universe also fades into brightness at the very end. The phantom encounter, if a small black hole, say, the mass of a mountain compressed to the size of a grain of sand, were to pass through Earth, it would leave almost no trace. It would slip through the planet in less than a second, its gravity intense but brief. The chance of such an encounter is virtually zero, but it illustrates the scale of things, how something so powerful can also be so elusive. Danger in this sense is not always about destruction. Sometimes it is simply about invisibility. Lessons in cosmic balance. The existence of danger in the cosmos is not a threat, it is a teacher. Black holes, in their immense power, demonstrate stability as much as collapse. They recycle matter, drive galaxies, ignite quasars, and sculpt space-time itself. Without them, the universe would be dimmer, less structured, less alive. Even their potential for destruction is part of creation's balance, a necessary counterpoint to light, birth, and motion. It is harmony, written in gravity. Resting in the gravity of awe, if ever a black hole drifted near our world, the lesson would not be fear, it would be scale. For we are small creatures on a small planet, orbiting a modest star, within a galaxy that itself drifts like dust among billions. And yet, within that smallness, we have built tools that can hear the echo of colliding black holes across 1 billion light-years. We have turned our telescopes toward the edge of nothingness and seen its shadow. We have learned to measure silence and call it data. A black hole is the purest expression of gravity's authority. It is not a monster, but a law fulfilled completely. Its presence reminds us that the universe does not bend to our comfort. It bends to truth. And that truth, strange and relentless, is still beautiful. If one were to come near, the balance would shift, yes, but even that shift would be a continuation of cosmic order. Gravity is not cruel. It is precise. It follows the same mathematics that guides the moon around Earth and keeps your feet anchored to the ground. The same equation that draws stars together into galaxies could, in another scale, draw galaxies into darkness. And both are acts of the same universe. Creation and collapse as two sides of one rhythm. Look up at the night sky. Every point of light you see is both fragile and eternal. Stars are born, live, and die. And from their ashes come new worlds, new chances, new eyes to gaze upward again. Even black holes in their silence play their part. They recycle the remains of dead stars, sculpt galaxies into spirals, and whisper energy back into the cosmos through gravitational waves and Hawking radiation. They are the universe's way of remembering what once was and transforming it into what will be. Every night sky we see is a promise kept, that despite the violence of cosmic evolution, balance remains. Planets still orbit, stars still shine. We exist in the thin calm between collapse and expansion, a quiet harbor in an ocean of motion. So when you close your eyes tonight, imagine that balance, the invisible fabric of space-time gently flexing beneath every step you take, the orbit of the moon syncing with your tides, the heartbeat of the cosmos pulsing faintly beneath the hum of your own. Even the most powerful forces in the universe rest. Even black holes, once fierce with collapse, sleep in the farthest corners of existence, slow, patient, dissolving into light over unimaginable eons. Their danger becomes peace. Their silence becomes harmony. They too are part of the great exhale, and so are you. You are made of the same matter that fell into their gravity billions of years ago, reassembled into breath, into warmth, into wonder. You are a continuation of that same story, a small bright consciousness looking back at the stars and daring to understand them. Rest easy now, traveler of the cosmos. Let gravity hold you the way it holds everything, firmly, gently, without judgment. The universe watches quietly. And somewhere beyond the reach of light, the black holes, dangerous, beautiful, eternal, hum their soft gravity song, a lullaby for all existence. This is the end of the broadcast, or maybe just the edge of another beginning. For as long as there have been eyes to look upward, we have watched the stars and wondered if they ever watched back. Every telescope, every equation, every midnight thought is our way of sending a message into the dark. We are here. We see, we want to understand. And somehow, across the vastness, the universe has answered. In the bending of light around a black hole's edge, in the whisper of gravitational waves traveling through space-time, in the quiet pattern of atoms that built our bones, it all speaks back not in words but in balance, not in sound but in rhythm. You are part of that rhythm. You are one heartbeat in the long pulse of creation, a note in a song written in the language of gravity and time. Tonight, as the noise of the day fades, you can feel that rhythm beneath everything. The slow turning of the earth, the distant shimmer of galaxies, the patient hum of existence itself. Let it remind you, you are not separate from the cosmos. You are the cosmos remembering itself, and so this transmission ends, not with silence but with continuity. Another night, another orbit, another chance to listen. Until the next signal, sleep gently under gravity's song. The stars are still watching, the universe is still unfolding, and you, traveler of light and dust, are still part of the story. Good night.